Struby, and this is a reading of wave properties. Amplitude. Can you describe a wave? For a water wave, one way might be to be able to tell how high the wave rises above or falls below the normal level. This distance is called the wave's amplitude. The amplitude of a transverse wave is 1/2 the distance between the crest and the trough as shown in figure 6. In a compressional wave, the amplitude is greater than the particles of the medium that are squeezed close together in each compression and spread farther apart in each rarefaction. This is figure 6 here, and we have the crest, the trough. The amplitude is the distance between this rest position, this flat line. Amplitude and energy. A wave's amplitude is related to the energy that the wave carries. For example, the electromagnetic waves that make up a bright light have greater amplitude than the waves that make up dim light. Waves of bright light carry more energy than the waves that make up dim light. In similar way, loud sound waves have greater amplitude than soft sound waves. Loud sounds carry more energy than soft sounds. If a sound is loud enough, it can carry enough energy to damage your hearing. When a hurricane strikes a coastal area, the resulting water waves carry enough energy to damage almost anything that stands in their path. The large waves cause the hurricane to carry more energy than the small waves or ripples in a pond. This picture here is looking like a hurricane is washed onto this boat. The devastating effect of a wave with a large amplitude can be seen in the aftermath of a tsunami. Tsunamis are huge sea waves that are caused by underwater earthquakes along the faults of a seafloor. The moment a seafloor along the fault produces a wave. As the wave moves towards the shallow water and slows down, the amplitude of the wave grows. This tremendous amount of energy tsunamis cause great damage when they move ashore. That part is about tsunamis. Big earthquake sends a big wave, and it causes damage on the shorelines. Wavelength. Over here we see in figure 8 about different wavelengths. So it talks about here another way to describe wave is by wavelength. Figure 7 shows wavelengths of transverse waves and compressional waves, which this is figure 7 here. Wavelength of the slinky from this point to that. Wavelength from crest to crest to trough, the transverse wave. For a transverse wave, the wavelength is just from top of one crest to the top of the next crest, or from the bottom of one trough to the bottom of the next trough. For a compressional wave, the wavelength is the distance between the center of one compression and the center of the next compression, or from the center of one rarefaction to the center of the next rarefaction. Electromagnetic waves are wavelengths that range from kilometers for radio waves to less than the diameter of an atom for X-rays and gamma rays. This range is called the electromagnetic spectrum. Figure 8 shows the names given to different parts of the electromagnetic spectrum. Visible light is only a small part of the electromagnetic spectrum. It is the wavelength of visible light waves that determine their color. For example, the wavelength of red light waves is longer than the wavelength of green light waves. And this figure here shows us radio waves have the largest wavelength, and then down here gamma rays have the shortest wavelength. Next page, frequency. Frequency of a wave is the number of wavelengths that pass a given point in 1 second. The unit of frequency is the number of wavelengths per second, or hertz. Recall that waves are produced by something that vibrates. The faster the vibration is, the higher the frequency of the wave is produced. And this part here talks about the sidewalk model, where we're showing that frequency, how many waves pass a certain point, and gives you the frequency. So the wavelength or the frequency up top here is not as intense as the frequency in the picture down below. So next talks about frequency and wavelength. Suppose that each person in a figure 9 represents the crest of a wave. Then the moment of the people on the first sidewalk is like the wavelength of 4 meters. For the second sidewalk, the wavelength would be 1 meter. On the first sidewalk, where the wavelength is longer, the people pass the pillar less frequently. Smaller frequencies results in longer wavelengths. On the second sidewalk, where the wavelength is shorter, the people pass the pillar more frequently. Higher frequencies result in shorter wavelengths. This is true for all waves that travel at the same speed. As the frequency of a wave increases, the wavelength decreases. Color and pitch. Because frequency and wavelength are related, either the wavelength or the frequency of the light wave determines the color of the light. For example, blue light has a larger frequency and a shorter wavelength than red light. Either the wavelength or the frequency determines the pitch of the sound wave. Pitch is how high or how low the sound seems to be. When you sing a musical scale, the pitch and frequently increases from note to note. Wavelength and frequency are also related for sound waves traveling in the air. As frequency of the sound waves increase, their wavelength decreases. Figure 10 shows how the frequency of wavelength changes from notes on a musical scale. So we have up here, we have frequency. Let me take a C note here. Middle C is right above 250, like 275 hertz. And again, hertz is the measure of frequency. Wavelengths here are measured in centimeters. And so the wavelength for that same note is 130. And notice as the frequency goes up, the wavelength goes down. Wave speed. Let's see how you figure those. You probably watch a distant thunderstorm approach on a hot summer day when you see a bolt of lightning flash between the dark clouds and the ground. If the thunderstorm is many kilometers away, several seconds will pass between when you see the lightning and when you hear the thunder. This happens because light travels much faster in air than sound does. Light travels through air at 300 million meters per second. Sound travels through air at 340 meters per second. The equation of any wave can be calculated from this equation. Frequency times wavelength equals the wave speed, written as this: V equals frequency times lambda. In this equation, the wavelength is represented by the symbol lambda, which is the Greek letter lambda. And this last little paragraph is interesting. When mechanical waves such as sound and electromagnetic waves such as light travel in different materials, they change speed. Mechanical waves usually travel faster in solids and slowest in gases. Electromagnetic waves travel fastest in gases and slowest in solids. For example, the speed of light is about 30% faster in air than in water. Well, this has been a reading of wave properties. I'm Mr. Ruby. I hope you enjoy. Like and subscribe on YouTube.